Testing. 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 Good morning and welcome to this webinar by Micrographics. My name is Aldred Boyd. I will be going through this webinar, Inventor Nastran Tips and Tricks. I hope you guys all enjoy and let's get ready for some knowledge. Okay, so just a quick introduction. So for those of you who have used Nastran, or for those of you who haven't used Nastran, just a little bit of a sort of a refresher. So what is Nastran? Inventor Nastran is a general finite element analysis package that Autodesk has got for engineers and analysts. Basically what it's done for, it's used to simulate stress, displacement, heat transfer, fatigue, and some more stuff there on models created in Autodesk Inventor or imported into Inventor. So now this is pretty important. If you've got a a model that comes from somewhere else, a different CAD package, it doesn't mean that you can't use Nastran. Inventor has got a fantastic converter or conversion process for models that come from other software packages or step files, sat files, IGS, to bring it in, import that model and then have it placed within Inventor. Now, Inventor Nastran is a plugin to Inventor, so you do not have to leave the environment. So if you are familiar with the Inventor environment, then you'll be able to very much easily get around in Nastran. I've always said that, when learning new packages, probably the most difficult thing to do is sort of get used to the environment that you are in, so the user interface. So, with that user interface, because it is inside Inventor, you should be able to get up and running on Nastran pretty quickly. Okay, so just the agenda. So we're going to go through the following topics. So just looking at some tips and tricks in the following. So modeling and setting up, for your Nastran environment. Idealization and meshing. Contacts, loads and constraints. How to view a model for easy access and selection. Performance tips, where to get assistance, and then just a bit of a conclusion to tell us, just to sort of recap what we have gone through. Okay, so in the first one, modeling. Before you actually even start anything in Nastran, one of the biggest things to do is plan. It's kind of like when you create a model in Inventor, you got to think about, where does this model go? Where's this model going? What am I going to do with this model? How am I going to change this model? And you've got to kind of think the same thing for a Nastran FEA model. So plan. I really do think that that's probably one of the most important parts, because if you don't plan, and we'll talk about it a little bit later when it comes to things like surfaces or mid surfaces, it does play a big part, and it does play a big part in how much time you take to create that analysis and create the results that you want if you don't plan properly ahead. So with that planning, one thing you can do is you can create model states. So model states is a new addition to Inventor, where you can have different configurations in the same part model, or even the different assembly. So before 2022, it was something called iParts and iAssemblies. One of the problems with that is it was just very difficult to manage, because you had all these different components which weren't residing inside the part or assembly. They were residing somewhere else on your hard drive, or in a folder in the same folder as your original part or assembly. Now, with model states, it's great, because what you can do is you can either maybe suppress components, which you do not think will affect the end result of your analysis that you're going to do, and you can suppress features as well. So just this little example over here, I've got those little inserts over there, and I just suppress it because I do not think it's going to vastly change my end results when I do run the analysis. So I've created two different model states over there. You can see they're primary and FEA, and in my FEA I've just suppressed those features over there. So maybe it's an emboss that you've got your company logo on there, or the name, and it's not going to affect the analysis. All it's really going to do is increase the time for you to output and get your results. Sometimes what you can do as well is you can combine the parts of the assembly. So if you've got a pretty simple setup, and you can see that, okay, you know what, if I combine these two components, I'm still going to get out the same results, or in the same ballpark of results that I'm going to get. What are the advantages of this? There's no contact. So if you've worked with Nastran before, or any other FEA package, you will note that if you need to have two components interacting with each other, so if the one pushes on the other one's got to get pushed away or deform, you have to create a contact to tell the program, okay, these two are stuck together and they need to move together, or they need to slide up against each other, or they need to actually separate. But when you start putting in things like contacts, it's going to up the calculation time. And when we're doing FEA, we kind of want to get the best result for the least amount of time calculated. So having sort of no contacts, by having one component instead of two or three or four, it does negate having contacts, which will allow the analysis to run faster. What you do is you also get smoother results. So at the bottom of here, you can see the color, the color between the two parts. In the middle over there where the circle is, you'll see there that the red, where the maximum stress is not very smooth, whereas in the single part over here, it's a much smoother transition, as you see the different stresses on the components over there. Okay. One thing you'll also find is that it's much easier to mesh parts. So with the meshing of parts, you might have, say, 10 different parts, and those parts might vary in size from very large to very small in comparison. So what happens is, normally we go say, right, this is the mesh that I'm going to have, and you have one size element, and that element will be Nastran will try and put that one size element on all your components. Now, when that happens is that element, maybe it's 25, and you've got now a component which is not going to be able to take a 25 millimeter element. So it will actually then just fail and say, sorry, but I can't mesh all the parts. And then you have to go and you've got to analyze your component and see why is it not meshing. So with one component, it will be much easier to mesh the parts and then, in essence, run your analysis. What are the disadvantages of modeling in one component or putting it into from a couple of different parts into one part? You have to use the same material for all the parts. So with this, if you're going to have vastly different materials with different, sort of properties, you might not get the correct result that you want. Also, when you want to view the results later, you cannot hide individual parts. Okay, so you're going to have to see everything in its entirety. Okay. So when modeling, if you're going to use surfaces or maybe thin bodies, because there is a fine thin bodies feature inside Nastran, rather don't. Rather create a surface model. So for example, if you've got an assembly and all your parts are made out of sheet metal, recreate that assembly as a surface model. Okay. If you use thin bodies, one of the biggest issues, and this is something that I think that Nastran needs to really improve on, is that if I find thin bodies and I need to go and change my model, so I'll go change my sheet metal or change the parts, whatever, in my original assembly. You come back to the Nastran environment and you'll have seen that your surfaces have actually separated from your model. Okay, and you'll have to go and redo the whole thing over again. So this is something that, if you know that you're going to be using a lot of surface in it, so you're going to have surface idealizations, rather recreate the entire model as an FEA model separate to your normal model. Okay, you'll find that you'll save so much time, especially when it comes to having to recreate or modify your component to maybe get different results to enhance your parts and assembly. Okay. Another thing that Nastran does is when finding thin bodies, it takes the average thickness. And in the next slide, I'll show you exactly, I'll show you an example of that. The analysis will be more accurate because, you're not taking the average thickness. You actually have to go and create a shell element with your surface model. You're also able to create less idealizations. Okay, so when you do have a surface model, you obviously create an idealization, maybe it's stainless steel and it's 2 millimeters. And then from that, you then are going to go and select all the different surfaces that has a 2 millimeter stainless steel idealization. Whereas if you just say find thin bodies, it will take each separate surface and create separate idealizations for each of those. Okay. You also have more control over the model. Okay, and that also comes back to where the model kind of breaks very quickly when you try and modify it. And then the analysis also runs much quicker. Okay. And that is because you have less idealizations that you've actually put in for this in this model. One of the disadvantages, and this is a very, very big one, the solid model's already created. You've already created the model, so why can't you just use, fine thin bodies? But if you take a look at the time it'll spend having to create that secondary surface model for your FEA, and then modifying it and running separate simulations, you'll find that the time spent modeling is much less than the time spent trying to recreate your Nastran analysis, especially if it is quite complex. Okay, so just the examples I wanted to show you with the fine thin bodies. So fine mid surfaces. So you'll see over here, just with this I-beam, that when you create the surfaces, you'll find that there's a gap at the bottom and the top. And also, if you take a look on the right-hand side of here on this mid surface, it's 8.06043, because it's taken an approximation of those surfaces over there. And what you also have to do in addition to this is you have to make sure that those two are in contact with each other, because they need to push against each other, with the forces. So you actually have to create an additional contact. Whereas if you take a look at this next example over here, I've modeled it up with surfaces and everything is joining. When I go and mesh these three surfaces over here, because they're touching, I've got an option to make the nodes touch each other between the different surfaces. So in this example over here, I don't have to go put in an additional contact or two additional contacts, which will then in effect also up the time that it takes for me to run the analysis. On the right hand side of the idealizations, you'll see there that the top two surfaces have a a thickness of 10, and the middle one is a thickness of 6.3. So you'll see there as well, I'm getting more accurate results because my thicknesses are more accurate. They're the exact ones and not an approximation of the three surfaces or idealization that I've created. One thing you can do as well is just when you're working with these surfaces, sometimes you've got lots of parts and lots of surfaces. It's very difficult to see what's going on because they're see-through. So what you can do is you can make them not see-through or sort of opaque. And to do that, what you can do is you can select on the surfaces in your part model and you can take off translucent. Okay, so then you can see on the right hand side it actually looks like it's not see-through. It looks like a part. It's a bit easier to see. Now that is kind of a one-off. So if you had to do that, then you'll have to do it for every single model. Okay. So another option is to have it as opaque surfaces from the beginning before you start modeling. So if you do model up surfaces and then you go and put on this opaque surface under construction, it's only for newly created surface, not for anything that you've created previously. So before you start modeling, you go to your File, Application Options, Parts tab, and then under your construction, just tick opaque surfaces, and then when you draw it up, it's going to not be see-through. If you don't want to do that, then there's another way to do it is by changing the visual style. So, and that visual style is technical illustration. That's on the right hand side over there. You'll see there it's now not see-through anymore. Okay. Then some things that you can do in your environment setup. So you've bought a new laptop or a new computer, you've got like 24 processors, and your Nastran is still very slow when it does the calculations, but I mean, it should be multi-threaded. So what's happening over here? So the default for Nastran is that it only runs between 2 or 4 processors. So we need to up that. And where do we do that? We can go to our parameters. So in the parameters, it's right at the bottom of your history browser, or your tree. And you'll see that you've got your parts, analyses, and then at the bottom you've got model. And under model, you'll see your parameters. If you select that, you're then able to then go and change under your file management directory. Oh, sorry, not that one. Under your program control directives, you'll see there's end processors. So you just up that, and then that will change the amount of processors it's going to use when running the analysis. And then another problem that you might occur is when you're running the analysis, it actually comes to the point and says, sorry, I can't run it anymore. I've actually run out of disk space. Now, when Nastran runs the analysis, it writes out files to your local drive. And in that local drive, obviously, if you don't have enough space because it's filled up with other stuff, it can be a problem. So what you can do over here is you can actually write it out to a different location. So if you've got 2 drives, maybe you've got a C drive and your D drive. Your C drive is used for, your programs, and your D drive is used for your storage space for any models that you've got. Direct your file specs under File Management Directives. Direct the file spec to your D drive or some drive that has got a lot of space for it. Okay. Now, when you do change these, this is for the current model only. So that, when you do open up a new part or a new assembly and you run your Nastran, then you'll have to go and do this again. So what can we do to be able to just do it once and then that's it, we can leave it and we run it until obviously we upgrade to maybe 2024, 2025, or 2026. So if you want to change the parameters for this, then what we do, we go to C drive, program files, Autodesk, Nastran, Inventor Nastran 2022, 2023, 2024, and then the Nastran folder. And you can go browse down to the nastran.ini file. So this is where all your settings are. And with that, just basically open it up with Notepad, Notepad++, whatever you want to use, and then go browse to the different. So here you can see on the right-hand side, file spec. That's where the files are being kept. That's the temp folder. And then, for your processes, just go find that parameter in processes over there. Now, just with this, where it writes the files to, just also take a note of where that folder is. Because sometimes, you might be working and you'll think, oh, why have I got so little space in my, on my hard drive? Sometimes Nastran will not automatically delete those files. So just go to that folder over there and just go make sure that all the files have been deleted. Another little bit of a tip over here, or a bit of a trick actually, is the prompt for solutions with warnings. So when we're running our analysis, you might come up to this message that you see on the left over here. Nastran file cannot be created due to the following errors. You go to details and it says no constraint exists within subcase. Now, if say for instance you're doing a transience analysis, it doesn't need a constraint. Or maybe you know that, look, that constraint that's missing over there or whatever is missing, it's not going to actually really do much to my end result. And you're aware of this maybe because you've done this analysis before without this constraint or without the warning that it's giving you or the error. And it does work. It gives it to give the result within the same ballpark that you are gonna, that is going to work. So what can we do with this? If you go to your default settings, under your general option, you'll see there prompt for solution with warnings. If you tick this, so by default it's not ticked. If you tick this prompt for solutions with warnings here in the middle, then what happens is instead of giving the message on the left where it just allows you to close, it'll give you the message on the right saying that, look, the model contains the following errors and may not run correctly, but would you like to continue anyway? So yes, I would like to continue because I know it's going to give me the correct results or in the ballpark of the correct results I'm expecting. Click on yes and it will run your simulation. Okay, so at least with that, you're able to then sort of see what not have to go and now analyze the model, see exactly where this error is, because the error might be like a node or something like that. Or, if you've ever worked with Nastran, it gives you these funny error codes, E5000, E10000. You don't know what's going on. Just say, listen, right, ignore, run the simulation. I'm happy with what the results will be. Another thing that also really slows your computer down is when doing these analysis is all the arrows, like for your forces, your loads, your constraints, etc. Now, that's because they're drawn up in 3D. Now, yes, it's very pretty, and if you've got the most expensive graphics card, yes, it might run smoothly, but maybe not as smoothly as if these arrows were actually 2D. So to optimize the graphics for when you're turning it around, you can go to your general settings again, and under display options, just tick on optimize graphics for fast rendering. So that is off by default. And you'll see the picture on the left has got your 3D arrows. The picture on the right has got 2D. So it will change it to 2D and be much quicker when navigating around your model. Okay. Okay, so on the idealization size, okay, so one thing that Nastran is fantastic at is running an analysis where you've got different types of idealizations, be it solid, linear, or surface idealizations. They work very, very well together, and it's very, very good at sort of passing the forces through from one idealization to the other. Whereas you find that some FEA packages, like if you had to use the normal Inventor FEA package, it's not very good. If you've got a part idealization, you've got a surface idealization, they don't really gel very well. So this is what Nastran is actually very, very good at. Now, talking about idealizations is choose the best idealization for the part that you're actually working on. If it's sheet metal and it's sitting on two sort of square tubes or something like that, for the square tubes, use your linear, and for the sheet metal, use your surface. Okay, you'll just have to make sure that the contacts are correct so that the forces get sort of pushed through. And that would be the quickest way to run the idealization. But that is, basically get Nastran do the legwork for you. You just need to choose, what's the best option to make the FEA run as quickly as possible. Because that's really our goal over here. You want to get the most accurate result, but being able to do it in as quick a way as possible. Maybe you don't have great hardware or something like that, so you've got to choose the correct idealization for that. Okay. Now, you get solid idealization. That's probably the slowest idealization to sort of have an analysis run. Then obviously shell idealizations will solve quicker than solid, and linear idealizations will solve quicker than both shell and solid idealizations. Okay. Then meshing. So meshing is also very, very important. If you've got a bad mesh, you will get a bad result. So please be very, very careful of that. If your mesh size is too big, you'll also get an inaccurate result because it's just not very accurate if you don't have more sort of nodes to compute the results from. But obviously, if you have too many nodes, it'll take too long to do the analysis, and the result will be very similar than if you had used sort of bigger meshing or where you get less nodes. Now, if I take a look at what we have available, so initially you'll just creates a mesh setting. So a mesh setting is one element size for everything. So if you've got 100 parts, it'll be, in this example over here, element size is 38. It'll put a maximum 38 element size on every part. Now, if those parts, you've got smaller parts, bigger parts, and you've got different, that 38 might be too big for some of the parts because they're small in comparison to bigger parts, you will then have to, it will not actually mesh. Or when it does mesh, because you've got maybe continuous meshing on, it can't fit the nodes on the two different parts together because maybe you can't mesh one of the smaller parts. When that happens, then we have to go to something called the mesh table. So what the mesh table does is it will discard your mesh settings, and it will then rather use the mesh table to go mesh and do your analysis on. So with the mesh table, what I'm allowed to do is I can actually, for the different components, have different size mesh elements. Over here you can see I've got 4 different parts, and I can put 4 different, so the top 2 I've got the same size, and then the bottom 2 I've got 2 different sizes. Now if I sort of run the mesh and I think, okay, you know what, for this one part I just need to go a bit smaller or a bit bigger because maybe it's quite large and the mesh is a bit too small, the calculations are run a little bit too long, I can just go to that component, and on the right hand side of here next to the magnifying glass, I'll just tick that, change my size, and then generate the mesh, and it will just generate the mesh for that part. It won't run everything through again. A nice thing about this as well is that you can go and just click on the magnifying glass and it will zoom to that component over there. So you can see, exactly what's happened, because if I run my mesh or generate the mesh for everything, if it can't generate a mesh for any of these components, instead of that green tick, it'll be a red cross. Then you can go zoom to that, go check out what the part is, and then say, okay, right, you know what, say this is, there's a problem over here, and figure out exactly how you're going to remesh this. If you've got to do an analysis on a component or an assembly and it either comes from someone else or maybe, maybe someone did it in the past and you have to redo the calculations because something went wrong and you have to just find out exactly why. One of the things you need to take a look at is what mesh was used to run the analysis, because was it the mesh table or was it just the mesh settings? And if I go to this, you'll see there, you right click on the mesh model, and you'll see there either there'll be a tick next to either mesh table or mesh settings, and then you'll just say, listen, right, use the mesh table or use the mesh settings. The reason I don't have a tick next to this is that I think I've only got one model in this over here, so it's not going to show me which ones it's using because it'll be both the same for each one. So yeah, so that's just a nice, you know exactly which mesh was used, so that you can also then go and just change that, either the mesh table or the mesh settings, to rerun an analysis. Okay, on to connectors now. So you might have seen something called connectors if you have worked in Nastran before, and you'll wonder, what is this? What does it do? Why do we have it? Now, connectors are used to create things like rod elements, bolts, springs, or just rigid connectors. And why do we do this? So for instance, if I've got bolts and nuts, and say you've got your assembly and you put 1,500 nuts and bolts in, so that's 3,000 parts, which if you have to then go and do an idealization for that, it's going to be 3,000, it's going to have to idealize 3,000 parts, and when you run your analysis, it's going to have to do calculations on those little 3,000 parts that you've got over there. And that's not very conducive when you're trying to get out these results as quick as possible. So what you've got over here is you've got the bolt connector, and the bolt connector really does simplify down what the bolt is. So you can literally suppress all the bolts and nuts that you've got in your component, and then you can go and just add these bolt connections to that. It would be nice if maybe you could convert those bolts to connectors, but I'm sure someone has put that up on the Nastran idea station for Autodesk to look at. So with these bolts over here, one thing you don't want to do is, and this is something that I know sort of not a lot of people do know, is that under your connector element, if you go create a nut and bolt, and you go click on OK, then you've got to go to the next one and you click on OK, what's going to happen is in your sort of browser under your bolts connectors, you're going to find that you've got, for instance, if you had 1,500 bolts connections, you'll have 1,500 connectors. Now, if I have to go modify that because maybe the bolt is too big or too small, I've got to sort of put a new one in. Having to change that maybe bolt diameter, I'll have to do it 1,500 times. So what we can do with this is, just to speed up the process, is once you've selected the two edges where your bolt and nut is going to be connected to, on the two different parts, just click on next. And then what it does is, what you'll have to do is just clear the bearing surface for the bolt head and clear the bearing surface for the nut, and then select the two new edges for your nut and bolt. And then you go click on next and you run through that. So what's going to happen is, you'll have one bolted connector and you'll have your 1,500 bolts over here. And if you have to modify it, you just have to change your bolt diameter over here, which will then update all 1,500 much quicker. Springs as well. So how do we model up a spring? You don't want to have to actually go model up a spring, and also it'll be a bit difficult because it won't accurately show the forces maybe over there. So what we can do is we can just put a spring connector in over there between your two different points, and then put in the appropriate stiffness for it. Okay. So what happens if we have, say for instance, an engine or motor mounted on a component? Okay, so this is something that does come up a lot, is you've got or a heavy mass, you've got something heavy sitting on a component, on a skid or something like that, and you want to go and analyze that. What you could do is you could find the model of it, of the motor, bring it in, put it down on the skid, and then run idealization of that. But if you have to run an idealization on a big motor, it's got lots of curves, and it's going to be a bit difficult, or it's going to take a very, very long time for Nastran to run that analysis, just to calculate how the forces are going to run through that. So you want to kind of simplify it down as much as possible. And for that, we can use what we call a concentrated mass. So that concentrated mass is found under your idealization. And what we'll do is, we just need to put that concentrated mass on where your center of gravity is going to lie of that component or that motor. So what I've done over here is the concentrated mass is the green and gray block over here. And what we can do is we just create a work point. So just a normal work point in Inventor, and then we'll specify that the concentrated mass sits over there. And what you'll notice at the bottom is I've got 4 holes in this piece of sheet metal over here, or the surface idealization. Now, the mass sits at the top, the holes sit at the bottom, and we now have to make sure that we have the forces running from that motor, or the mass of that motor, the weight, runs through those 4 different holes. So what we've got is the rigid body connector. And that rigid body connector will just select all the holes, and then we make sure that we select, so the dependent over here will be the holes, and the select points over here will be where the center, where the concentrated mass will be sitting. Okay, so then it kind of connects those and acts as a rigid body. Now there's 2 different types of rigid body you got. So you got rigid, and this is if the motor is more rigid than the frame. So your bolt holes will move around, sort of as the frame moves around as well. Or you got interpolation, and what this does is it ignores the stiffness of the motor, and the mass will get distributed to the 4 holes depending on the position of the mass relative to the holes. So is it in the middle? Is it a bit more to the one side, to the other side? It'll distribute the mass in accordance to where it is sitting over there. Okay, so the next part we're going to go onto is contact. So this is kind of now where we've got a whole lot of parts in an assembly, and with those parts we need to make sure that they're all connected, so that when you put a force on the one, if it's touching the other, it will then move or deform it in the way that it's supposed to. Okay, so these contacts, what do? They connect parts together to transfer your load. Okay, and there's 3 different types of contacts you've got. So your auto, so it finds any 2 faces that are in contact with each other, and it creates a manual contact. Okay, it is efficient, but what you probably will have to do later is actually go through every single one of them and modify them manually, because it can only do one. It doesn't know what contact to put in. Is it bonded? Is it does it slide up against it? Does it separate? So normally what we have got is everything will just be bonded, and then you'll have to go and sort of analyze every single contact until you find and say, will it separate? Will it slide up against each other? Then you've got the manual one, and this is either selecting faces or edges that will be in contact with each other and saying exactly what it is. Is it bonded? Does it separate? Does it slide? It is better than the solver that you've got. when there's a large sliding motion. So I'll talk about the solver now, but and this is also very time consuming. But is it more time consuming than the auto? Yes and no. For instance, in the auto, if I need everything to be bonded, I just do it once, it's done, I can move on and run the simulation. But if I have to, after running auto, go find all the different sort of contacts and say maybe it's sliding or it separates, then it can maybe take as much time as the manual does. And then you've got the solver. So solver is kind of a combination of auto and manual. So you'll go off and you go put, sort of contacts on everything, manual contacts, and you say, hey, actually the rest of it needs to all be bond contacts. So what I'll do is I'll just run the solver. I don't have to select anything, but it doesn't override the manual contacts that I've created. So the auto, it sort of works a little bit differently to that. One thing I do get asked about is symmetric contact versus unsymmetric contact. Okay, so that's just how the two surfaces interact with each other. And just something to keep in mind between some unsymmetric and symmetric is that with the unsymmetric, your secondary nodes contact your primary faces. So depending on what you select first, will either be primary or secondary. With unsymmetric, there are fewer elements to calculate, so it is a bit of a faster solution, but it's not very good with sharp edges. So think of a pyramid coming to the top. So you've got two surfaces coming to the top to a point, and you've got another block maybe coming and sitting on top of it. It's not very good with sharp edges. You're not going to get a very good result with that. Whereas in symmetric, okay, both secondary and primary faces will be in contact with each other. There are all more elements to calculate, so this will be a more slower solution, but it will be more accurate as well. But it is also very good with sharp edges. So that is one of the, so just keep in mind symmetric versus unsymmetric when you are doing your simulations, or your contacts, sorry. Okay. One thing that you can also do over here is when selecting face edge vertices. Normally, we start our load, we start our constraint, and then we start clicking, and actually to select the points, I need to select the line, so it's right click, select other, and then you start cycle through the different options that you've got over there. If you open up the load, the dialog box over here, if you right click on the select entities, what will happen is it'll give you a little right click menu and allows you to filter out, just select faces, just select edges, just select vertices, or face chain as well. So maybe you want to put a load on surfaces which are in contact with each other with tangent edges. It'll then select all those various surfaces over there. Okay. Another thing that you might not be aware of is pressure versus force. So if you use pressure instead of force, it is quicker to generate the Nastran file. Okay. So if you are running a simulation and you've got a lot of force loads applied to your model, then try and use a pressure load instead, because it will run that Nastran file quickly. So this is, remember, all of these tips and tricks are trying to get us to run an analysis as quickly as possible, and this is something that will assist you over here. Okay, so if you're running an analysis and you've got a lot of different subcases, okay, and with these subcases you have to have the same loads or constraints applied in the subcases. What you should do first is create the subcases. So create the subcases first, and then go apply all your loads and constraints. So when you have created your subcases, and then say you've got 15 of them, then you go, okay, right, create this load over here. At the bottom, when you create that load or constraint, you'll see there it will list all the different subcases, and just go select the ones that this is going to apply to. So then it applies it all very, very quickly. To do it the other way around, it's very tedious. I think you have to go down to your part at the bottom and drag up all the different loads and constraints that you have created in your different subcases. So if it's going to be loads and constraints which can be shared across different subcases, do not create them inside the individual subcases. Rather, create the subcases, then go to the load, create the load, and apply it to the subcases that you've got. Location of specific nodes. Now, I know I've had this happen to me many times. You're looking at your results, and it tells you, look, there's a warning at node X, Y, and Z. This force over here at X, Y, and Z is a problematic. Now you've got to go find that, and in your, from the results that you get from analysis, I mean, there could be like hundreds of thousands of them, but how do you know exactly where in space this node is or this face is? So what you can do is go and create the UCS at that XYZ coordinate from your model space. So from your model tab. So go to the 3D model, go to this UCS over here, and then go and type in your X, Y, and Z value, and then create that work point. And that work point will be at the node that has been specified from your results. So, it's much easier to find out exactly where that is over there. Okay, so the one thing when viewing your model, so if you've got a lot of components and you want to see what's forces or pressures or deformation you've got on a specific parts, if you've got a lot of components and you can't really see it, how do we control the visibility? So the two different ways to do it. You can control visibility of CAD bodies, mid surfaces, offset surfaces, FEA entities, concentrated masses, connectors, constraints, coordinate systems, free edges, loads, material orientations, mesh and mesh controls, all through your object visibility, which sits in your ribbon. So go to that, and if you don't want to see the CAD bodies, untick that. Okay. You can also have browser access for that, so you can go there, right-click on mesh, or right-click on the part one, and hide or display the body. Okay. So there are two different ways of that. And as always, with Autodesk and their software, they always give you more than one option to be able to do certain functionality. Yeah. And then just for for performance and being able to run this a little bit quicker, there's two differences over here for displays and post-processing. So you can take off automatic plot updating and also undeformed edges. Okay, so just take that off. You won't be able to see it. It just also runs it a little bit better. So just once again, trying to be able to run the analysis quicker, trying to move it around and see it just a little bit quicker over there. Okay, and then just the last one to take a look at is the help files. So with the help files, it's either online or offline. With the offline, you do run the chance of not having things updated. Nastran and Inventor and actually all the Autodesk products, they're always sort of updating. They have dot releases now, which will have additional functionality, bug fixes, etc. And with that comes the addition of extra help files or an addition to the help files. So if you have offline help files, yes, it's great. I mean, you're going to be offline, use that. But just note that if anything additional is added to that help files, just go and download the newer help files for that. But if you're on the online help files, then everything will be updated, whether it goes from 2023.1 to 3 or 2024, which has just been released now. And then the Nastran forum. So, one of the best things, and, this is not just with Nastran, with Inventor, AutoCAD, whatever software you are using, Autodesk, the community is a great help. You've got a problem, come to the forums over here, post up what you want, and, inevitably someone will try and help you. If you do not get help on the Nastran forums, then, we can escalate it up through to Autodesk as well. So with every subscription that you have or license that you have with Autodesk, you do also get assistance from Autodesk as well. So it's reactive support and not proactive support. So if you've got a problem with something, you can then go find assistance from somebody in Autodesk. And they might just tell you, well, look, it's a problem with the software, we need to fix it. So you'll get a bug fix out of it. Or they'll say, okay, look, these results might not be correct. Let's go take a look at the coding and see exactly why it's not happening over here. Another nice thing about this is, and this is whenever anything comes out or an update comes out, you'll see at the top there's an article by John Holtz, Inventor Nastran, list of changes. So whenever there is an update, dot release or major release, you'll see there that there's this list of changes that he puts up there, and it will then go and, if you're getting maybe a different result or something's not really working like you can see there just why it's not doing that. So there's a very comprehensive list of changes that he puts up over there. Okay, so just in conclusion, plan. Really, please do this. It's not nice having to do modifications to a model and then everything explodes, when you go back to your Nastran environment. Use the appropriate idealization. If you use the correct idealization, you'll get better results, and as well as the analysis will run much quicker. Don't model in 3D if there is a tool in Nastran for it. Things like springs, bolts, rigid connectors, concentrated mass. Switch off graphics you don't need. Go from your 3D graphics to your 2D graphics, and use your Nastran forum online for any issues that you do have. Okay, great. Thank you very much. Are there any questions? Okay, if there are no questions, thank you very much for watching this webinar. I hope you guys have a great Friday and weekend. Cheers.